Welcome back to another Math 3 video. So our packet says, you may remember a task from last year about the famous race between the tortoise and the hare. In the children's story of the tortoise and the hare mocks the tortoise for being slow. The tortoise replies, slow and steady wins the race. The hare says, we'll just see about that, and challenges the tortoise to a race. In the task, we model the distance from the starting line that both the tortoise and the hare traveled during the race. Today we will consider only the journey of the tortoise in the race. Because the hare is so confident that he can beat the tortoise, he gives the tortoise a 1 meter head start. The distance from the starting line of the tortoise, including the head start, is given by the function d of t equals 2 to the power of t, d in meters and t in seconds. The tortoise family decides to watch the race from the sidelines so that they can see their darling tortoise sister Shelley prove the value of persistence. So number 1 says, how far away from the starting line must the family be to be located in the right place for Shelley to run by 5 seconds after the beginning of the race? So 5 seconds is going to be when t, I want that a little bit better. It's going to be when t is equal to 5. So we need to find what d of 5 is. And that's going to be 2 to the 5th power. So our distance is going to be 32 meters. And then they want to know how far do they have to stand if they want to see or pass after 10 seconds. So that's when t is going to equal 10. We want to know what d of 10 is. That's going to be 2 to the power of 10. Your distance is 1,024 meters. Next it says, describe the graph of d of t. Shelley's distance at time t. What are the important features of d of t? So I went ahead and made a graph of this. So this is a graph of d of t. All right. So if we're looking at this, we can tell right off the bat that this is an exponential. It follows that exponential curve where it looks like that. Also, we can just tell it's an exponential from the function. And let's find the domain. All right. If we look at the domain of this guy, right, he continues on this way and then just continues to grow. So the domain here would be all real numbers. However, specifically for this scenario, you can't have negative time. So in this very specific case, it's going to be 0 to infinity. And the reason for that is we just don't want to put in negative time. And then for the range, if you look really closely right here, it hits the y-axis at 1. So our range would be 1 to infinity. And the reason for that is because we have kind of a restricted domain because we don't want time to go negative. All right. All right, so let's go ahead and move on to number 3. It says, if the tortoise family plans to watch the race at 64 meters away from Shelley's starting point, how long will they have to wait to see Shelley run past? So for this one, they're asking for us to go backwards, right? They want the distance to be equal to 64. So we're going to say 64 equals 2 to the power of t. Now, in order to actually solve this mathematically, you would need to use logs. We don't necessarily have to do that. We can kind of just test it out, right? We can even make a chart here. We know 2 to the power of 1 is going to give us 2. 2 to the power of 2 gives us 4. 2 to the power of 3 is 8. Power of 4 is 16. 32. Then 64. So they're going to want to be, actually they're going to have to wait 6 seconds if they're at 64 meters. So our time would be 6 seconds. So I just did that by making kind of like a little function table of this function. How long must they wait to see Shelley run by? If they stand 1,024 meters. Well, you know what we can even do? Let's look back here. If they stand 1,024 meters away, they're going to have to wait 10 seconds. All right. And that's just, we already calculated that, right? We found that, if they wait 10 seconds, they have to be 1,024 meters away, and vice versa. If they're 1,024 meters away, they're going to have to wait 10 seconds. All right. So next it says, draw a graph that shows how long the tortoise family will wait to see Shelly run by at a given location. So when it's a given location from her starting point, that tells us, if that's what they're giving us, that's our independent variable. And that means if that's the independent variable, that's going to be our x value. It's going to be on the x-axis. All right. So let's go ahead and make a chart. We kind of already started to do this. And we're going to do this backwards. We're going to say, okay, well, where will she be at time 0, 1, 2, 3, 4, 5, 6. All right. And we're just going to plug in to d equals to t. So if we plug in 0, we get 1. We plug in 1, we get 2. Plug in 2, 4. And we kind of talked about this already, so I'm just going to fill them in. 8, 16, 32, 64. All right. So we can go ahead and fill this in. So we'll go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All right. So now we'll go ahead. We're going to plug in the point 1, 0. So 1, 0 would be right about here. And we've got 2, 1. That's right about there. 4, 2. Really, we're not growing too fast here yet. Then we've got 8, 3. Sorry, we'll get there. I'm just trying to make it look nice. There we go. 8, 3. And then we've got 16, 4. 32, 5. And 64, 6. We'll go right there. So as you can see, this grows really slow compared to an exponential. All right, that would be our graph. And this is the inverse. Okay, so I want to point out that this is the inverse of this. Okay. Next it says, how long must the family wait to see Shelly run by if they stand 220 meters away from her starting point? So, one thing I want to point out here, let's go ahead and let's add some more points to this chart here. Okay, so we'll do, she's 7, 8, 9. So at 7, it'll be 128, 256, and 512. So again, you kind of have to, if you want to actually solve this, you have to use logs. But we can go ahead and look at our chart. If they're standing 220 meters away, they're right about here. So we can estimate and say they're going to have to wait between 7 and 8 seconds. All right, so we just went ahead and put some more points in there, and we're just kind of estimating for that one. So for number 7, it says, what is the relationship between d of t and the graph that you have just drawn? How did you use d of t to draw the graph in number 5? So the relationship is going to be that they are inverses. Right, we just talked about their inverses, and we created that graph by swapping x and y, right? So this used to be the x value, this used to be the y value, and we swapped them. We made this the x value, right? We plotted those points on the x-axis. and this was our y value. For number 8, it says, consider the function 2 to the power of x. So before we had kind of a restricted domain, right, because we didn't want time to go negative. That's why we started at 0. But now they're just talking about the function in general. They're talking about this entire thing that continues on where we can have a negative x value. So it says, what are the domain and range of f of x? So we go ahead and we look. The domain of f of x would be all real numbers. Then the range, I'm going to go back up, is going to be everything bigger than 0. We don't go negative here. There's, I kind of drew that. It's going to continue on this way, and it's going to stay above that x-axis. So our range is going to be 0 to infinity. 0 is going to get an open bracket because there's like an asymptote there at 0. So it's never going to actually hit the 0 mark. And then it asks, is it invertible? So just as a refresher to check to see if something is invertible, I'm going to go ahead and draw a graph of it. You do the horizontal line test. So you check to see if you hit 2 points when you draw horizontal lines. In this case, yes, it is invertible because it doesn't hit 2 points when I do the the horizontal line test. Next, it says graph f of x and f of x inverse on the grid below. So I'm just going to kind of do a little bit of a rougher graph, but I want to point something out. So this was our f inverse, and this was our graph of f of x. All right. One thing to point out, this is reflected over the line y equals x. All right. So you always reflect over the line y equals x. Now it says, what are the domain and the range of f inverse? So if we look, this guy will go down this way. And the domain is going to be 0 to infinity. For the inverse graph, there is an asymptote there at 0. But this time it runs vertically. Then the range of this graph is going to be negative infinity to positive infinity because this goes down. It follows, this graph is going to follow the asymptote all the way down. All right. So next, it says, if f of 3 equals 8, what is f inverse of 8? So kind of to reiterate, this is your x value, this is your y value, right? So the point is 3, 8. And they want to know, okay, well, when your x value is 8 on the inverse, what's going to be the y value? Well, remember, we swapped the x and y values. So you could say f inverse of 8 is going to have to equal 3. Next, if f of 1/2 equals 1.414, what is f inverse of 1.414? So again, this is our x value. This is our y value. So the point was 1/2, 1.414. And they want to know, okay, well, what happens when we input 1.414 into the inverse? Well, again, we swap the x and y values. So it would be, I guess we could write f inverse of 1.414 equals 1/2. And it says, how do you know? Well, we're swapping the x and y values in the inverse. Now for 11, it says, if f of a equals b, what is f inverse of b? Will your answer change if f of x is a different function? So, again, our point is just a comma b. So in the inverse, it would be b comma a. So f inverse of b equals a. And will your answer change if it's a different function? No. All right. Basically, by the definition of inverses, you have to switch. Well, let misspelled that pretty badly. X and Y values. All right. So now I'm going to go ahead, I'm going to do a couple of problems from the Ready, Set, Go, just because I figured there's going to be a lot of questions on these ones specifically, and I kind of want to give you a little bit of help. All right, so I want to point out for number one, when you have the same base, you're able to just set these equal to each other and solve. So you would do x plus 1 equals 2x minus 3. Okay, so when you have the same base, you can just set them equal to each other. I'm not going to solve that. I figure you could solve that on your own. For number 4, if you look, we don't have the same base here, but we can make it the same base. We can rewrite it. We're going to keep the 3 the same. We're going to keep that as 5x minus 4. But I could rewrite that 9, to be 3 squared, right? 3 squared equals 9. So I'm just going to replace the 9 with a 3 squared. And then I can multiply the 2 and the 2x minus 3. So I end up having to distribute. So I get 4x minus 6. So we get 3 to the power of 5x minus 4 is going to equal 3 to the power of 4x minus 6. So all I did there was replace the 9 with a 3 squared, and then I multiplied the 2 powers. All right. Now I have the same base. Once you have the same base, you can set these equal to each other. All right. I'm going to go ahead and solve. So I do minus 4x, minus 4x. I get x minus 4 equals negative 6. Add 4. I get x equals negative 2. All right, so that is how you do number 4. So for all of these, you want to make sure that you get them in the same base. You can get 8 into base 2. You can get 81 into base 3. You can get 4 into base 2. So make sure you go through and try and solve those. All right, and then I want to do a couple from down here. So let's go ahead, let's do 24 and 25. Now, I will say I'm kind of going to run out of space. I didn't feel like they gave me enough room here. So I'll do 24, and then I'm going to kind of scroll down and do 25. So what they want us to do here is plug in a plus b into h. So this is my h function here. So I'm going to go ahead and do h of a plus b equals, and then I need to plug in a plus b wherever I see an x. So I need to plug it in twice. So we're going to do a plus b squared plus 3 times a plus b minus 10. So now I need to go ahead and solve this. I need to FOIL this guy, distribute this guy. So I got a plus b times a plus b. I get a squared plus ab plus ab plus b squared. And then I'll go ahead and distribute. So I get plus 3a plus b. Oh, sorry. Plus 3a plus 3b. Because I need to distribute. Minus 10. And then we can combine these. They're like terms. So we would have a squared plus 2ab plus b squared plus 3a plus 3b minus 10. All right. And this is what h... Oops, that doesn't look pretty. H of a plus b equals. All right. So that would be your answer to number 24. So now let's go ahead and try, go ahead and try number 25. All right. So they're asking for h of g of x. So what this means, since g of x is on the inside, that's what I'm plugging in. All right. And that means that I need to go ahead and take this and plug this in there and plug this in there. So I'm taking the entire function g of x and plugging it in wherever I see an x in h of x. So let's go ahead and get it written down. So let me write 25 and we are doing h of g of x. So we will go ahead and plug in 2x plus 5 squared plus 3 times 2x plus 5 minus 10. And again, we need to FOIL this, distribute this. So we've got 2x plus 5, I'm going to go ahead and zoom in now, times 2x plus 5. And when we FOIL that, we get 4x squared plus 10x plus 10x plus 10. And then we got to distribute. So we get plus 6x plus 15 minus 10. And there's a couple of like terms we can combine. We can combine these guys and we can combine these guys. So I get 4x squared plus, oh, actually we can combine these guys as well with the 10s. So we get plus 26x. Oh, and this guy got to go with the constants. And then when we add those together, we get plus, oh, you know what? Here, I just realized I made a mistake. 5 times 5 is 25. I apologize. I put a 10. I did 5 plus 5. So that should be a 25. Then we need to combine our constants. So we get plus 30. I do apologize for that. All right, so we get h of g of x is going to equal